Hello friends, welcome to my lecture on languages and grammars. This is second lecture on this topic. Regular expression, let us define. So, a regular expression is used to represent sets of strings in an algebraic fashion. Let sigma be an alphabet. Okay? A regular expression R over sigma is a special type of string coming from sigma with 5 new elements. So, the 5 new elements are this left bracket, this right bracket, star, then or, this symbol denotes or, and then lambda. Okay? The expression R and the language LR, okay, over sigma are defined as follows. There is no regular expression of length 0, that is first thing. Okay? These are the rules. There is no regular expression of length 0. The regular expression of length 1, okay, and 1 are. Let us consider the regular expression of length 1. Then there are regular expressions of length 1 we have as lambda and every a belonging to sigma. So, whatever a belonging to sigma you take, they are all regular expressions of length 1 apart from lambda, and L of lambda, okay, language over lambda is the set containing lambda, while language over a is the equal to set containing a. Okay. So, that is how we get the language LR when R is equal to a. The only regular expression of length 2 is this left bracket right bracket, because you can see we have left bracket right bracket. So, they are counted 1 each, 1 plus 1 2. So, regular expression of length 2 is this left bracket right bracket, nothing else. So, the language it defines is the empty set phi. Okay. So, phi is denoted phi denotes this regular expression of length 2, okay, the language with no elements. Now, let R be a regular expression defining a length L, then R is a regular expression and LR equal to LR. R star is a regular expression defining the language L star. Let R1 R2 be regular expressions defining the language L1 and L2 respectively, then R1 or R2 is a regular expression defining the length language L1 union L2, and R1 R2 is a regular expression defining the language L1 L2. In the absence of parenthesis, in order to evaluate a regular expression, the hierarchy of operations are: first we take up this star, then we take up the concatenation, and third we take up OR. Okay? Third is we take up R. So, let A be sigma equal to A B be an alphabet, then A belongs to sigma. Okay? A belongs to sigma. So, A is a regular expression. A is a regular expression, and when A is a regular expression, A star is a regular expression. Okay. Now, A B belong to sigma. So, A and B are regular expressions. So, A or B is a regular expression. Now, A or B is a regular expression. So, A or B star is also a regular expression, and this is a regular expression. Okay. So, then A star, A or B star, this is also a regular expression by the properties of regular expressions. Okay. Now, A belongs to sigma. So, A is a regular expression, and therefore, A star is a regular expression, and so A star is a regular expression, and here we have A or B. So, A and B are regular expressions. So, A or B is a regular expression, and therefore, A or B star is a regular expression. Okay. So, A star, A or B star, A is a regular expression. Now, here A and B are regular expressions. So, A or B is a regular expression, and therefore, A or B star is a regular expression. Now, here we have A or phi. Okay. A and phi are regular expressions. So, A or phi is a regular expression, and therefore, A or phi star is a regular expression. So, A or B star and A or B phi star, okay, is a regular expression. So, they are regular expressions over sigma. let us say sigma equal to AB, determine whether or not each R is a regular expression over sigma, and if it is, describe LR. So, R A is there in element in A belongs to sigma. So, A star A is a regular expression, and therefore, A star is a regular expression, and L of A star, L of A star will be equal to lambda A and so on. Okay. So, that is nothing but lambda A square A cube A to the power 4 and so on, because L of A star is nothing but the union of L of A star is equal to L of A star equal to lambda A. So, this is lambda A square A cube A to the power 4. Now, when we consider second case R equal to A star, since A is a regular expression, A star is a regular expression. So, A star is a regular expression, and L of A star will be equal to A, and then for A star we have lambda A square A cube and so on. So, we will have, now let us take the concatenation. So, A lambda, that is A, then A, so then A square A square, so A cube, then A4 A cube, so A4 and so on. Okay. Now, R equal to AB star, so L of R, okay, L of AB star. Okay. So, A and then B star is lambda B square B cube and so on. So, L of AB star will be A lambda, that is A, AB, then AB square, AB cube and so on. So, that is L of AB star. Then A is a regular expression, B is a regular expression. So, B star is a regular expression. So, A or B star is a regular expression. Okay. Now, L of A or B star. So, this will be equal to A or B. Okay. So, B star. So, B star means lambda B square B cube and so on. Okay. So, this is A lambda B square B cube and so on, that is L of A or B star. Now, in the case fifth, A and then this notation. Okay. This notation is not defined in the case of regular expressions. We have only 5 special type of strings. So, this star, then R and lambda. So, this is not there. Okay. This is not, this symbol is not there. So, this is not a regular expression. These are not a regular expression. Let us define what do you mean by a grammar. A grammar is a set of rules to define a valid sentence in any language. A sentence is made up of a noun phrase followed by a verb phrase. That is, sentence is made up of noun phrase and verb phrase. A noun phrase is made up of a noun or an article followed by a noun. A verb phrase is made up of a verb followed by an adverb. Thus, noun phrase is made up of article and noun, verb phrase is made up of verb and adverb. Thus, we can say that a sentence is made up of an article, noun, verb, adverb. If we associate the actual words, say with the article we associate A, with the article we can also associate the noun, we can associate with boy, and then with this noun we associate dog, and with verb we associate runs or walks, and with adverb we associate quickly or slowly. Then some sentences in the language could be a boy runs quickly or the dog walks slowly. So, here in the sentence a boy runs quickly, A is the article, boy is the noun, runs is the verb and quickly is the adverb. So, this sentence is made up of an article, noun, verb, adverb. Similarly, in the case of the second sentence, the dog walks slowly, the is an article, dog is a noun, box is verb and slowly is the adverb. Now, let us discuss a phase structure grammar. Okay, phase structure grammar or simply grammar. Okay, G we can denote it by G. It is defined by a 4 tuple G consisting of Bn, Bt, S, P, where Bn stands for a finite set of elements called variables or non-terminal symbols. Bt, this N means non-terminal symbols and this T denotes terminal symbols. So, Bt is a finite set of terminal symbols and clearly the intersection of Bn and Bt should be phi, because Bn consists of non-terminal symbols and Bt consists of terminal symbols. Among all the non-terminal symbols in Bn, okay, there is a special non-terminal, we denote it by S. Okay. It is called the start symbol. Now, P is a finite set of ordered pairs alpha beta, usually written as alpha goes to beta, where alpha and beta are strings in Bn union Bt such that at least one of the alphas, okay, contains a variable. Variable means an element of Bn. Now, terminals are denoted by lowercase letters of the English alphabet A, B, C, okay, and variables are denoted by the capital letters of the English alphabet A, B, C. S denotes the, as we have already said, S denotes the start variable. Alpha beta denotes the words in both variables and terminals. Now, there is a notation which we shall be using, alpha goes to beta 1, beta 2, beta n. It means that alpha it means that it consists of the notations alpha goes to beta 1, alpha goes to beta 2, alpha goes to beta n. So, all these alpha goes to beta 1, alpha goes to beta 2, alpha goes to beta n can be represented in terms of a single implication, alpha goes to beta 1, beta 2, beta n. This is just for the sake of convenience. Now, let us say Bn, which is the set of non terminal symbols, okay, consists of A, B, S. S is the start symbol, and Bt, which is the set of terminal symbols, consists of A, B, and P is the set of productions, okay, which consists of S goes to A, B, A goes to A, B goes to B, B, A goes to A, B goes to B. Then P can be expressed also as P equal to S goes to A B. So, this we can write as such, S goes to A B. Now, here you can see that A goes to A, also A goes to A. So, by our previous notation where we have said that if alpha goes to beta 1, alpha goes to beta 2 and so on, alpha goes to beta n, then they can be represented by a just one notation, alpha goes to beta 1, beta 2, beta n. Okay, so, using this A goes to A goes to A can be represented as A goes to A, comma A, and similarly B goes to BB, okay, B goes to BB and B goes to B can be written as B goes to BB, comma B. So, this is for the sake of convenience that we write P in this manner. Now, let us consider the language of a grammar by applying the production rules. Okay. The production rules are the elements of P, okay. The elements here, S goes to A B, A goes to A, comma A, B goes to B B, comma B, these are production rules. So, by applying these production rules in a different order, okay, a given expression can normally generate many strings. The set of all such strings is a language defined or generated by the grammar. Now, if W and W dash are any two words in Bn union Bt, then we say that B goes to B, W implies W dash if W dash can be obtained from W using one of the productions, that is if we can find mu and nu such that W equal to mu alpha nu and W dash equal to mu beta nu, where alpha goes to beta is a production. So, we shall say that W goes to W dash provided we can find mu and nu such that W is equal to mu alpha nu and W dash is equal to mu beta nu and alpha goes to beta is the production. Now, we also say that W goes to star W dash if W dash can be obtained from W using a finite sequence of productions. Okay. So, using a finite sequence of productions, if W goes to W dash, then we write it by the notation W goes to star W dash. The language of G is denoted by LG, okay, and it is the set of all W belonging to BT. BT, as you recall, BT is the set of terminal symbols. So, W belongs to BT such that S goes to star W. S is the start symbol. That is, LG consists of all words in the terminals that can be obtained from the start symbol S by the above process. Now, let us see the following example. Consider the grammar G in example 2 show that W equal to A square B4 belongs to LG, the language determined by G. Let us see what is the example 2. This is example 2. So, Bn is ABS, Bn is Bt is equal to A comma B, and the production rules are P equal to S goes to AB, A goes to AA, B goes to BB, A goes to A, B goes to B. Now, we have to see whether W equal to A square B4 belongs to LG. Okay. So, we start with S. Now, when we will say that W belongs to LG, let us go to the definition. The language of G is denoted by LG, and LG consists of all W belonging to BT such that S goes to star W. S goes to star W means we can reach W by using a finite sequence of productions starting with S. So, let us see, we start with S. Okay. Now, S goes to, you can see here S goes to AB. So, we write AB here. Okay. Now, what we want? We want ultimately W. W means A square B4. A square B4 means AA, BB, BB, BB. Okay. So, that is AA means A square, BB, BB means B4. Okay. Now, let us see how we will reach there to AA, BB, BB. Okay. If you simply write A goes to A, B goes to B, then AB will goes to AB and we will not reach here. So, we cannot directly use A goes to A, B goes to B. What we should do? We should use A goes to A. Okay. A goes to A, then we will write A goes to A and B goes to BB. B goes to BB. Now, what we can do, because we just want two A's here, so we can use the this production rule A goes to A, then AA will go to AA and BB. B can now be replaced with again BB because we want 4 B's. Okay. So, B can be replaced with BB. So, BB B. Okay. Now, here now if you replace this B using this production rule B goes to B, we will have only 3 B's. Okay. So, we again use this production rule B goes to BB and we will have AA, BB, BB. Now, we can use this production rule B goes to B and we shall have AA, BB, BB, which is equal to A square B to the power 4. Okay. So, this is W. So, you can see we have reached W using a finite sequence of production rules starting with the start symbol S, and therefore, W belongs to LG. Okay. So, W belongs to LG. Now, describe the language LG of the grammar G in example 2. Okay. Let us see now what kind of elements could be there in LG. LG is equal to set of all W such that S goes to star W. Okay. So, let us see what we have here. B n equal to, again we will have to write the values of B n, B t and P. Okay. So, B n equal to A B S, B t equal to A B, and production rules are P goes to P production rule, P is set of productions, P is equal to S goes to A B, then we have A goes to A, we have B goes to B B, and then we have A goes to A, B goes to B. Okay. So, we start with the symbol start symbol S. Now, S goes to A B. Okay. One thing could be that we straight away replace A, this A with A and this B with B. So, we will have A B. If I replace A with A, B with B using these two production rules, I will get A B. So, A B is an element of LG. Okay. Else what we can do, S goes to A B, now A goes to A goes to A B. Okay. Again A goes to A we can write. Okay. So, we will have A square A square B. Okay. Again we can say this goes to A square B. So, we will have A cube B. Okay. Now, if I replace A with A, I will have A to the power 4 B. Okay. Then B goes to B B. I can straight away write use this production rule, B goes to B, then I will have A 4 B, or I can also do A 4 B goes to A 4 B B, and then I can say I can, if I replace B with B, I will have A 4 B square. Okay. Or what I can do, A 4 B B B, okay, which will give me A 4 B B square. If I replace B by using this production rule B, I will get A 4 B cube. I can also continue further, and from here A 4 B B square, which will take me to A 4 B B B square, and I will get A 4 B B cube. Now, if I use B goes to B, I will get A 4 B B cube. So, that will give you A 4 B 4. Okay. So, what we will get? We can get A B, we can also get like here we had A square B. Okay. I could have used A here, I could have used the production rule A goes to A, then this would have given A cube B. So, this LG consists of elements of the type A to the power m, B to the power n, where m n are positive integers. So, all such elements are there. Okay. Minimum value of m and n could be 1 each. Okay. So, we will have this, as we have seen, A B belongs to L B. So, m and n, if both of them are equal to 1 each, then we will have L G A B belonging to L G. Other we can also have A square B or A B square, or we can have A cube B square, like that. So, a to the power m, b to the power n are elements of LG where m and r positive integers. So, this language of the grammar G is given by this LG. Now, let us see another example. Let B n be equal to S A B, B t equal to A B, P is the set of productions, S goes to A B, B goes to B, B goes to B A goes to A B. Then let us see what is LG. Okay. So, S goes to A B. Okay. Now, if I replace B with V directly, okay, I will have A B. So, A B belongs to W, A B belongs to LG. Okay, because A B is obtained from S by a finite sequence of production rules. Now, another thing could be S goes to A B and then B goes to B A. We can use this, B goes to B A. Okay. Now, if I replace now A can be replaced with this A B by using this production rule. So, this goes to A B A B. Okay. Now, if I use this production rule B goes to B, then what I will get? A B A B. Okay. Right. So, by taking B goes to B, I will end up with A B A B. If I do not do that, okay, so from here I can also do A B A B. If I do not use this production rule, I use this one, then what I will get? A B A, B goes to B A. Okay. Now, A goes to A B. So, let us use that. So, A B A B, A goes to A B. Okay. Now, B goes to you can replace B goes to you can replace B with this B. So, then that will give you A B A B A B if you use this one. If you do not use this one, you use B goes to B A, then here in place of B we shall have B A will be replaced with A B and then B can be replaced with B. So, we will have this is A B cube and this is A B square. Okay. And if you use instead of B goes to B, you use B goes to B A and then A goes to A B and then B goes to B, we shall have A B to the power 4. So, so here LG is A B raised to the power n is a positive integer. So, this is the language determined by G in this case. Now, let us look at this determine LG if B t equal to A B C, P equal to this. So, here B n, here B n is A S. Okay. The non-terminal symbols are A and S. S is the start symbol, A is another non-terminal symbol. And B t is A B C, P is the set of productions like this. So, S goes to here, you can see S goes to A S B, S goes to A S B. Now, A S goes to A, okay? A S goes to A, okay? So, we have A A B. Now, what we can do? So, one thing could be that A B directly A B now will have to go to C. So, C is an element of LG. Now, here we can also do one thing, instead of replacing A S with A, I could have done S goes to A S B and then again I use production rule for S, S goes to A S B. Okay. So, then what I will get A square S B square, A square S B square. Now, if I now I can use S goes to again S goes to A S B. So, then this will be A A cube, or I can write it as because I need to have one AS, so that yeah, okay. So, AS I can now write A square AS B cube, okay. So, AS now goes to A, okay. So, A square AA B square, okay. Now, AAB goes to C. So, this goes to A square C B square, okay. So, you can see here we have on left side of C we have A square, on right side of C we have B square. So, powers of A and B are same, okay. And here also if you can if you use this ASB you replace AS by AA, we got this C. So, here power of A is 0, okay. This is nothing but A to the power 0 C B to the power 0. We can also get ACB. How we will get ACB? Let us see, S goes to ASB, okay. If I replace S by ASB, I will have the powers of, okay, let me see, ASB, okay. And then what I can do, AS I replace with AA, okay. So, we will have AA B square, but then AAB will be going to C, okay. This is nothing but AAB B, okay. So, this goes to ACB, okay. So, S goes to ASB, okay. S now can be replaced with ASB. So, we get ASBB, okay. Now, we can use this AS goes to AA, okay. AS goes to AA means this goes to, I should write, this goes to A, ASB goes to yeah, AS goes to A, okay. So, A B square. Now, one B we have to take from here. So, AAB B, okay. AAB goes to C. So, we get ACB. So, this we can see that by using these production rules we will get on either side of C, okay, the same power of A and B, that is here A square, here B square. So, we will have Lg equal to A to the power m C B to the power m, where m is a non-negative integer. So, this is the problem where we have taken Bn to be As, Bt to be ABC and the set of production rules P, and we found Lg. Lg is the set of all elements Am, C, Bm, where m is a non-negative integer. So, like this we can find the language determined by the grammar G. With this I would like to end my lecture. Thank you very much for your attention.